Okay, y'all know that this is not the way I normally like to teach, but it's what I have to work with because my iPad is not connecting very well. Proof by induction. Essentially, what you're doing is making an assumption about one case and then proving that it applies for every case after that by doing, like, typically it's k plus one. So if you imagine a line of dominoes, if you have one domino and you knock one over, that's the basic step. It's the starting point of this process. So if I knock one domino over, then the next domino falls, which we'll call that domino k plus one. Um, and then the next domino falls, and the next domino falls, so on and so forth until I put down the k domino, the final domino, which is called the inductive step. When you do proof by induction, the most important part is if you make that assumption, if you use this basic premise, you have to use that in your proof, or else it doesn't count as proof by induction. Like if you prove something and then don't use it, then you've done something wrong. So once you prove it, you have to use it. So normally I would be writing this out and explaining it step by step, but instead, since I can't really write, and I know y'all don't want to deal with me trying to write with my trackpad on my keyboard. um, I'm just going to go through this with you. So we're going to prove with mathematical induction that 1 plus 2 plus 3 plus every other number up to a certain number, and then plus all of those numbers back down again, is equal to n squared. Now this is pretty similar to our, we did another proof like this earlier on where we added two sets of sums to show that it was equal to n squared. So this should feel pretty familiar, but we're just coming about it a different way. So the first thing we're going to do is come up with our basic step. So we're making a statement where we need to prove that for certain values of n, that it's true, that this idea is true. So we're going to start with the most easy one to prove, which is when n equals 1. So if n equals 1, that would be 1 plus all the numbers up to 1, which is just 1. So it's just 1. On the right-hand side, 1 squared is also 1. So I've proven that the left-hand side is equal to the right-hand side. Therefore, when we plug in just 1, this statement is true. So now I need to prove that it's true for some value of k. So essentially what I'll do is plug in k instead of the letter n. And then I'll do k plus 1. And then I'm going to factor it out so that I get to use what I found before. So here we have, I've made my assumption that it's true for k. And then in the inductive step, I have to use the assumption to show that the statement is also true for k plus 1. So when I go through this process, now the first part here, where's my annotate? This first step here is to say that you're just plugging in k plus 1 instead of n. So all of the numbers up to a certain number and back down again. Once we go through that process, we can combine like terms, and what essentially ends up happening is we get k squared for just that first sum, which is something that we proved before when we used 1. 1 is equal to n squared. So the 1 is equal to 1. And then when you simplify it, you end up getting k plus 1 squared. Since p of 1 was shown to be true, and it's also shown that if the statement is true for some n equals k, it also must be true for n equals k plus 1. And then based off of that, if it's true for one, any number, and any number after that, then that means that it must be true for all numbers. I know that's very confusing, but if you walk through the steps, hopefully you will catch on. Okay, following that same premise, a much simpler version in my mind are ones where we talk about multiples and divisors. So if we're proving that 11 to the nth power minus 6 is a multiple of 5. So that means if it's a multiple of 5, it's 5 times some integer. So then I'll try it where n equals 1. So 11 minus 6, that's true. It is equal to 5, and 5 is divisible by 5. So then I'd use that same proof. So I'm going to make the assumption and make 11k the subject of my formula. From there, once I have 11k minus 6 is equal to 5b, that's the same thing as 11k is equal to 5b plus 6. And then my inductive step is now to then apply that same concept to k plus 1. So I have 11k plus 1, which when you use your laws of exponents, remember when you're adding two exponents, that's the same thing as multiplying them separated. So I would do 11k times 11 times 1. They just put it in the opposite order. So they have 11 times 11k, but it's the same thing. Minus 6. And then this is what I was talking about, where you have to use the step that you already learned. So we learned that 11k, we just stated up here in our assumption that 11k is equal to 5b plus 6. So we plugged it in right here. So at this step, here we have 5b plus 6 plugged in for 11k. And the reason I knew to use that is because I used it up here. So that's my assumption. So I had to use my assumption in order to make this true. I continue on by solving the equation, and then I get 5 times 11b minus 12. Now 11b minus 12 has to be an integer. So 5 times any integer, it's just another variable. We could call that c if we wanted to. So it goes to follow by the principle of mathematical induction that no matter how many times, how many powers I raise this, if it was k plus 3, k plus 5, it would follow that same principle. Okay, so I know all of this was really complicated, but I'm hoping that just doing it yourselves will start to make sense. So the proof by induction, I just did groups of 3 this time. So group 1 for problem A is going to be Bella, Nock, and Sonia. For part B is Tomas, Leonard, and Andrew. And then this third problem about using mathematical induction to prove that it's divisible by 8 is Rohan, Liz, and Jacqueline. So at the bottom, again, I included extra problems for extra practice, just to make sure that you guys are getting it down. Yeah, that's the best I can do for you guys. I'll try to answer as many questions. I know it's very confusing, but the best way to learn this one is just to start doing it. So best of luck with your problems.